Okay, let's dive into this. Welcome to today's explainer. We're officially cracking open the Week 2 system design blueprints, and today it is all about figuring out how databases actually work under the hood. We're talking pure database fundamentals here. We're going to take all these high-level concepts and translate them into the concrete architecture you absolutely need to understand. We're looking at how data physically lives, breathes, and functions within a well-designed system. So let's get into it. Here is our roadmap for today's explainer. Think of it as our blueprint to building a high-tech data vault. First up, structuring data with tables and relationships. Second, connecting that data. Third, speaking SQL. Fourth, the ironclad rules of ACID. And finally, some hands-on practice. All right, moving right along to part 1 of our blueprint, structuring data, focusing specifically on tables and relationships. So I really want you to think of a database table as a highly organized digital filing cabinet. We've got a very simple structure set up right now, just an ID, a name, and an email. But this right here, this is the exact spot where raw, chaotic information transforms into structured, manageable rows and columns. Every single row is a distinct record, kind of like one physical file folder inside that huge cabinet. And every column is a specific attribute of that record. It's clean, it's logical, and honestly, it is the absolute bedrock of system design. But, well, here's the catch. A single table all by itself is just a silo. And a single filing cabinet locked away in a dark, empty room isn't exactly useful to anyone, is it? In any robust, real-world system, your user table absolutely needs to relate to your orders table, and then that orders table needs to relate to your products table. They are fundamentally designed to interact with one another. It's like a giant puzzle where all the pieces have to fit together perfectly. Which naturally leads us to a pretty crucial question. How do these tables actually talk to each other? I mean, if we have a perfectly structured user table sitting over here and a perfectly structured orders table sitting over there, how on earth does the system know which user placed which specific order? Well, that brings us to section 2 of our syllabus, connecting data with keys. This is where we get into these specific tools that build those relationships we were just talking about. Now, what's really interesting about this concept is how elegantly it solves our relationship problem. We use primary keys and foreign keys. Let's break that down. A primary key is your unique identifier for a record. It is the absolute truth of that row. Basically a digital fingerprint. Absolutely no two rows can ever share the same primary key. No way. On the flip side, the foreign key is the bridge. It's a column in one table that points directly back to the primary key in an entirely different table. That is the exact mechanism of our relationship. Literally, it's how the orders table reaches out and says, hey, this particular order right here, yeah, it belongs to user ID number 5. Okay, shifting gears to phase 3 of our blueprint, speaking the language. We're talking about SQL. We've built the architecture, now let's talk about how we actually communicate with it. So SQL, it stands for Structured Query Language. The absolutely crucial point here is that SQL is the required vocabulary for our syllabus. It's how you query, command, and completely control the table structures and those key relationships we've just spent all this time building. Like, when you want to find all the users who bought a specific item, or maybe you need to update thousands of email addresses all at once, SQL is the precise, specific command you send into the system to actually make that happen. Moving into the climax of our explainer, Section 4, the ironclad rules of ACID. We are now officially securing the vault to make sure our data is actually reliable. But before we dive into the ACID acronym itself, we kind of have to understand what it's actually protecting, right? And that would be transactions. A transaction is a sequence of operations performed as a single logical unit of work. Let's make this real to your everyday life. Imagine you're out running errands and you use your debit card to buy a coffee. Money has to leave your checking account, and that exact same amount of money has to be added to the coffee shop's account, right? Those are two completely distinct database operations, but they must succeed or fail together as a single logical unit. Because if the money leaves your account, but, say, a network error prevents it from actually reaching the shop, well, then the system is fundamentally broken. And that coffee shop disaster brilliantly illustrates exactly why we need a vault protocol. To prevent that very scenario from ever happening, system designers rely on ACID. It is the absolute, unbreakable security protocol that protects those transactions we just defined. It ensures that no matter what kind of chaos happens on the server side, our data remains perfectly 100% valid. So let's break down this ACID acronym line by line, because this is the final, necessary layer of our data vault. A is for atomicity. This means all parts of the transaction succeed or absolutely none of them do. There are no half-finished coffee purchases allowed. C is for consistency, meaning the data must remain completely valid according to all defined system rules, both before and after the transaction happens. I is for isolation. If multiple transactions happen at the exact same millisecond, they do not interfere with each other at all. And finally, D is for durability. Once a transaction is finalized and committed, it is saved permanently. Even if the entire database system instantly loses power, that data is safe. These four ironclad rules are exactly what make relational databases so profoundly reliable. And that brings us to our final section, practice, focusing on PostgreSQL and MySQL. Time to take all this theory and put it to work. The source material for today's syllabus explicitly calls out PostgreSQL and MySQL as the primary environments where you should practice these new foundational database skills. And for good reason. Both are incredibly powerful industry-standard relational database management systems. Whether you choose the robust, highly compliant environment of PostgreSQL or you go with the renowned speed and web ubiquity of MySQL, the critical next step is taking all these concepts out of theory and dropping them into a real terminal. Go ahead and try building the tables and setting up those keys yourself. Write the actual SQL commands and execute your own secure transactions. Because now you possess the structural blueprints. You understand how to build the digital filing cabinets, you know how to bridge them with keys, how to command them with SQL, and exactly how to lock them down securely with ACID protocols. The foundation is officially poured. So taking everything we explore today, how will you design your first system? Thanks so much for focusing in with us, and I'll catch you on the next Explainer.